until now, we've been working with differential equations and their solutions without explicitly defining the concept. So let us do it now. So let us define it in a rigorous mathematical manner. So basically, recall that a solution of a differential equation is a function that turns it into a right equality, right? So, but then since the differential equation, it involves y prime, and if y of t is a solution, then at least we should be able to calculate y prime, so which means that y has to be a differentiable function. And then, of course, for every value of t, so the point t and y of t, it should, we should at least be able to substitute it into the differential equation. So, which means that this point, right, it should belong to the domain of the right-hand side. Well, but then in practice, when you just solve the differential equation explicitly, so sometimes y of t may or may not be defined for certain values of t. But then the intuition here is that a differential equation describes a motion, and a motion is continuous, right? So, which is why the domain of a solution is required to be an open, well, sorry, not necessarily an open now, but just an interval. Let me maybe give you an example. So, suppose that you solved the differential equation, and suppose that you got the answer is y of t is, say, I don't know, 1 over 1 minus t squared. Right? So, but then let's continue. So this is 1 over 1 minus t and 1 plus t. But in this formula, so t cannot be equal to negative 1 or to 1. Which really means that what we are looking at is not one solution, but rather three different solutions. So one of these solutions is 1 over 1 minus t squared, defined for t less than negative 1. So another solution is 1 minus t squared, defined for t between negative 1 and 1. And the third solution is 1 minus over 1 minus t squared, defined for t bigger than 1. And these three are independent solutions. They do not have to do anything in common. So they are just three different, because they describe three different motions. So one motion is defined when t is less than negative 1. Right? So then when t approaches negative infinity, y of t approaches 0. But when t approaches negative 1, this motion approaches negative infinity. But of course, if it approaches negative infinity, then it cannot continuously be transformed into the second motion, because the second motion approaches positive infinity when t goes to negative 1. All right. Hope this is clear. So here is the formal definition. So first order ordinary differential equation is an equation of the form y prime equals f of ty, where and now notice that I have modified whatever we've been doing a little bit. Now I'm going to require that the right hand side is defined on an open set. So the reason is analytic, because it's kind of more natural and easier to work with open sets. So also note that usually we require that the right hand side has continuous partial derivatives, unless otherwise specified. So we are going to see that the theorem of existence and uniqueness of solutions is only true, well, not only true, but it is true when the right hand side has continuous partial derivatives. Well, and then a solution of this differential equation is a differentiable function. Again, it is required to be defined on an open interval. Right? So the right hand side of the differential equation is defined on an open set in the plane. The solution is defined on an open interval. So the domain, in both cases, we require the domain to be an open set. well, this is basically for convenience of certain proofs. So let's go through a few examples. So here, the initial value problem, we can solve it explicitly, and we see that the domain of the solution is the whole real line, right? Because the right-hand side is defined for all values of t. Now, here is a bit trickier. Now, the domain now, so remember that the domain has to be a single interval. And if you look at the solution here, then you will see that the solution is undefined when t is 0, because so t cannot be equal, sorry, at 10 cannot be equal to 10, because if t is equal to 10, then we will have to divide by 0. So the right hand side will be 10 minus divided by 10 minus 10 to the power 10, but we cannot divide by 0, so this is not allowed, right? And since the our solution is undefined when t equals 10, it means that, well, the domain has to be either the interval from negative infinity to 10 or from 10 to infinity, because we need it to be an open interval, and it's just either this or that, because 10 is excluded from the domain. Well, but then note that the initial value of t, so the initial value of t is 0. And among these two intervals, 0 belongs to the interval from negative infinity to 10. So which is why it is actually the domain of the solution. Well, here is one more example. And this is an equation that can hardly be solved explicitly, but if you just look at the direction field, so you will see that there are two equilibrium solutions, and of course, so our solution has to be entirely between the two equilibria, so which means it cannot, leave this strip between 20 and 110, and since it cannot do so, we can extend it indefinitely to the right and to the left. So which means that the domain of this solution of this initial value problem is the whole real line. Okay, and now there is a little quiz on the domain